course, it's a multiple choice question. Anything that asks you on sigma notation would definitely be multiple choice. So let's take something familiar and write it in sigma notation. It's a bit like translating from one language to another. And the first thing is we use Greek letter sigma, that's a capital sigma, to represent the same thing that we do with the elongated s with the integral. It's a sum. Now, let's think about what we're doing when we're integrating. When we're integrating, we're doing a mathematical process that's equivalent to calculating the areas of a whole bunch of rectangles. Now, when we do it in integration, there are going to be an infinite number of rectangles on that interval, 2, 5. For our purposes, I'm going to imagine a total of 10 rectangles. So we're adding up rectangles. Well, how do you calculate the area of a rectangle? Well, it's length times width. So in this case, it's y times delta x. And we can go further. What is y? Well, y is just going to be x cubed times delta x. So you notice immediately how it corresponds to the integral. Now, the other parts don't correspond quite as easily. So the first order of business is that I need to capture this information that says I am only doing 10 rectangles. And what we do is let's assign each rectangle a number. The most common number is k. So like the first rectangle, the k would be equal to 1. And the second rectangle would be k equals 2, k equals 3, all the way up to k equals 10. That would be the very last rectangle that we're computing. So on the sigma notation, we write down here below the sigma, k equals, and we're going to start at number 1 every time. And then we use what's called a counter. Doing that, we're saying, okay, k is equal to 1, then 2, then 3, and 4, and 5. And up on top of the sigma, I'm going to put 10. And so this k and that 10 are related. K equals 1 is always basically our starting point with the first rectangle. And then we identify up here how many rectangles we have in this particular scenario. Now, in the same way that on the integral, we think of x cubed being the height of each one of those rectangles and dx being the width, the same is going to be true here. So this is going to be the height part, and this is going to be the width of each rectangle. Now, the width is actually easier to figure out on the front end than the height, so let's start there. So if we look at this graph, we see that the graph has 10 rectangles within that interval, and that interval length is 3. It's 3 units because we're going from 2 up until 5. And if I take that value, an interval of 3, and divide it into 10 parts, then I know the width of each one of those. The width of each one of those rectangles is going to be 3 over 10. It's like 3 inches divided into 10. So the width is really usually pretty straightforward to write. Now, 3 over what? Well, on k, whenever we start counting, we typically do it in terms of n, so I'm going to use that convention, 3 over n, and in this case, n is 10. So integrals are rooted in limits where the width of each of those rectangles is approaching 0. Sigma notation is rooted in the real world. So if we imagine what we are doing here, trying to add these individual rectangles up to determine the sum of the area under all of them, let's see what kind of a pattern we'd have to use. Well, notice first, the first thing we'd have to use is use a height of 2, because that's the x value, x of 2, because that's the x value where the integral begins. And we just do 2 cubed times the width. And the width we've already determined is 3 over 10. So now, what would be the value of the next x that we'd use? Well, it would be 2 plus a little bit. And that is 2 plus what? Well, if we think back to the problem, if the width of each of those rectangles was 3/10, and we started here at 2, then that would be 2 plus 3/10. Then what x would we use for the third rectangle? Well, that would be 2 plus 3/10 plus 3/10, because we'd have to move over 2 interval widths. And what's the next one going to look like? Well, it's going to be similar. It's going to be 2 plus, but we're going to have to add 3/10 3 times. So this is getting rather, long. So is there a way that we can kind of shorten this up? Is there a way that we can write a more general expression? And there is, because notice, in the second interval, we're adding 3/10, and in the next interval, we're adding 2 3/10, and in the next interval, we're adding 3 3/10. So we're going to write this with a counter. We're going to use the counter k with it going to a value of n. Actually, we'll just do the numerical part right now. So it should be clear that we have a value changing here, and it's counting from 1 and going up. 1, 2, 3, 4, 5. And how far would it go up? Well, for this particular scenario, it would go all the way to 10. And once you got to the 10th term, bam, you stop. That's the area under the curve. So within the sigma expression, we're going to have to show that, and that's going to be whatever the value of x is cubed, and the value of x is going to start with 2, and it's going to have a component added to it over and over and over. And the component that it's going to have added is the width of each one of those rectangles. And it's going to be counting from 1, 2, 3, 4, 5. So it should be clear the variable that we put in there to represent that counter is k. So that would be a sigma expression that represents the integral of x cubed evaluated from 2 to 5. So you know what sigma notation is? It's a way to take something simple and make it hard. Nevertheless, if you want to learn it, today's your day. Now, if you were given this general problem, compute the area under the curve from 5 to 13, you know exactly how you would set up your integral. Set up the integral going from lower limit of 5 up to 13, and then you just have the equation there, and that would be your integral. But let's make a sigma statement instead. And before we do, let's decide on how many intervals we're going to count. I think this time we should count 20 intervals. So that is, there are 20 individual rectangles that we would be summing up to estimate the area under the curve and therefore the value of the integral. So the first order of business is write a sigma, and now we know that we're counting from k, in this case, all the way up to 20. And we know that we are taking some equation that represents the height here and doing whatever with it. We'll come back to that. Now, again, sometimes it's easier to figure out the width way back here on the back of the problem before you figure out the height. So again, what's the width? Well, that's going to be 8 units from 5 to 13, and we're dividing it into 20 individual parts. So that means the width of each one of those individual rectangles is going to be 8 divided by 20. It's the length of that interval divided by how many rectangles are going to be in there. So now we start thinking about the individual substitutions that we'll be using for x. And what will the first substitution be? Well, substitution is going to be 5. So whatever we're putting in there is going to be 5 plus, and then it's going to be some interval. How big is that interval? Well, it's going to be 8 over 20 each time. But for every individual term, we have to add that 8 over 20 one time, and then 2 times, and then 3, and then 4 times. So we're going to put k in front of that because that tells us how many times we're going to be adding that 8/20ths. We're going to do it 20 times. Now, what happens to the 3 here in the original equation? Well, since a 3 is not being taken to a power or anything, we have 2 options. We could bring the 3 outside whatever it is we're computing for x. So just a reminder, this entire thing in parentheses, that's just what x is going to be equal to. So we could put the 3 there and then put the squared on the outside, fourth power on the outside of the parentheses, and see how that corresponds with y equals 3x plus, or 3x to the fourth. Now, in the same way that constants can move in and out of integral symbols, the same is true of this 3. We could take that 3 out front. I'm going to leave it there for now just so that it makes the connection between the original equation and our sigma notation. So there is a sigma expression that represents finding the area under that curve. So see, it's not too hard. You just have to know where the bits and pieces are. So let's do a different one. Let's do one where I give you the sigma notation and then you write the integral. In other words, I showed you how to drive forward and you drive backwards. So try this one on this side. You can just pause the video for a moment, see if you can turn that into an integral statement. So it doesn't matter which order you do these things in, but since it comes first, I think I'll do the limits of integration. So there should be a lower limit of integration and an upper limit of integration for this integral. And we should be able to see right there in the parentheses, because the parentheses is going to give that initial value of the x that we substitute in, and then it's going to add little portions as it moves to the right, and it's going to add them a certain number of times, in this case k. So that means the lower limit of integration is going to be 3. Now we can also see important information here when we talk about the width. When we think about the width of each one of those rectangles, it was a width of 2 divided by 10. What does that tell us then? That means that each one of those intervals was increasing by 2 over 10, so that means altogether the length of the interval from 3 to the upper limit of integration has to be equal to 2. Now, what we have to be careful of is make sure that we say the interval length is 2, which means the x values go from 3 up to 5. So whatever is in parentheses and being increased by some small amount, that's always going to be the x of your integral. So that means we can also write the integral more completely, 5 times the natural log of x, and dx is kind of like the width. So these aren't terribly hard, they're just uncommon. And it doesn't really add much to our understanding of calculus. That's one of the reasons that I omit this. Okay? So if you want, I'll do one more example problem and then you're on your own. Because sigma notation questions are so rare on the AP exam, it's hard to know how they might structure a question. Here's what I think would probably be a reasonable AP exam question if they had it on. And that would be to give you an interval statement, and then ask you to select the equivalent sigma expression. So let's give that a shot. You might want to take a moment now, pause the video, see if you can't figure it out. Now when you first set up the integral statement, what's going to be n? Well, if we're referring to it as an integral, let's just say n is a number. We don't know what it is, but it's just a number. If we were taking the limit, that number would be infinite. That is, we would be computing the area of an infinite number of little rectangles. So try to proceed from here. So it should be relatively straightforward to write the height of each one of those rectangles and the width. Now in this case, since we don't know how many n's there are, we can only say the width of each rectangle is just 5 divided by n. Remember that 5 was how many units there were between the limits of integration, and if we subdivided it into n rectangles, then 5 divided by n would give the length of one of those rectangles. Now we tackle x. So instead of just x, when we're counting using sigma notation, we're going to start at a point, so that's going to be x is equal to 1, and then to that x, we're going to add some quantity over and over and over. And what will that quantity be? Well, it's going to be 5 over n. And how many times is it going to be added? We don't know exactly, but we'll put k in front of it to say, okay, we're counting. We're counting the first and then the second and then the third and so on and so forth.